Hello and welcome to today's webinar about Coreform IGA. We'll get started in about 30 seconds. All right, so I'm your host, Matt Cederberg. I'm the CEO of Coreform, and we're excited to share today's webinar with you about Coreform IGA, rapid simulation of multiple design iterations with Coreform IGA. So just last week, we were at the International Annual IGA Conference in Banff, Canada. So we met some of you there, and it's great to continue the conversation here. And with that, I'll turn the time over to today's presenter, Greg Vernon.
Yeah, thanks, Matt. And again, thanks everyone for attending today. And hello again to those that we met last week. So just briefly, what we're going to talk about today, we're going to just kind of help remotivate, why we're doing IGA, what the focus is, and then some of the key technologies that Coreform's developed for isogeometric analysis, our U-Splines and our flex representation method. And then we'll go ahead and give a live demo of how we can use Coreform IGA today to say do verification of topology optimized designs from the GE engine bracket problem, all in Coreform IGA, fully automatable and really robust. So, and then just as maybe before I start that, I think, Matt, we're going to allow for folks, if they have questions, they can put them into the Q&A in the webinar.
Absolutely. Yeah. Just throughout the webinar, we'd be happy to answer those.
Yep. Great. So as a quick background, again, to Coreform, we've really got two products that we're going to be showing today, Coreform Cubit and Coreform IGA. The former, Cubit, is a traditional FEA meshing program or software that we co-developed with Sandia National Labs. And we're enhancing Coreform Cubit to support isogeometric analysis. Some of the things we've been adding in there are our U-Splines into Cubit and the ability to export them to a format that a lot of folks who are doing research in IGA are familiar with, this Bezier extraction format, as well as we can prepare our flex representation models in Coreform Cubit. And then we're also writing Coreform IGA, which is a native isogeometric analysis solver from the ground up based on our technologies. However, we are leveraging modern high-performance computing and scientific computing libraries, such as PETSI, so that we can do massively parallel solves and be really performant. And then a quick intro just to some of the capabilities of Coreform IGA today. It's just a snapshot of a few of them. So in addition to maybe large information, we also have plasticity. We've got implicit dynamic and static solvers, as well as explicit dynamic solver. And then we also have contact, including self-contact. And then, I just don't have enough space to put more videos onto this slide, but hopefully kind of gives an idea for the realm that we're looking at. Okay, so to maybe kind of start with a motivating example, first with a kind of a traditional IGA or traditional finite element approach. So this is just a sample geometry from NIST. And we're just going to do we're going to apply some boundary conditions onto these legs to hold them fixed. We're going to apply a displacement on this little top nub, and then we're going to apply a pressure where these holes are on that flat surface. So again, in Coreform Cubit, we can do traditional FEA modeling. So this little video here is sped up to show that we can, for traditional hex meshing workflows, we're de-featuring our model, getting rid of fillets and conical surfaces that would be difficult to hex mesh. We can assign boundary conditions, or rather create surfaces and sets that we'll apply boundary conditions on. And then to be able to build the hex mesh, we decompose this complex geometry into hex meshable subregions. And then we can build our mesh and clean it up. We can evaluate element quality and all those fun things. So that process, took a fair bit of time. I think it probably took me maybe 10 minutes or so to build, maybe 16 minutes or so to build that mesh, and then sped up. And so then just why IGA is all that you saw there from me getting the initial geometry until I got that mesh kind of fits within this region here that starts with analysis solid model creation through the mesh manipulation region. And there's really no value added to the end customer of doing this process. In fact, by defeaturing the model, I might have actually removed value from the customer. Like the customer doesn't care how pretty the mesh looks. They don't care, any of that. They just want to know like what the results of my analysis are, what my engineering analysis are. And so the goal of IGA is to remove or minimize those portions of the model pre-processing step. And that's what we're focused on in Coreform. And so now taking the same model, but now using our flex representation method, which I'll introduce shortly, all we need to worry about is being able to build in an envelope domain. And so now this is only sped up, I think, like 50%. We're just going to, again, assign regions of our model to apply boundary conditions onto. So I'm going to say I want to apply boundary condition onto these legs. I want to apply a boundary condition onto this top nub. And notice how I've not done any defeaturing of my surfaces, which I did in the previous model. And then I can build my envelope domain where the computations are going to occur. And then I can, produce a mesh, can be quite coarse to begin with, and then it can be refined to get to whatever level of accuracy that we want in our result. But really, that's all that has to be done from a model prep standpoint. And so that's a really fast process. And we haven't had to, even out to this NIST embossment, we've even been able to leave in this model. And so then these are some results of the von Mises stress for this problem. You might notice that there's some tessellation or some kind of artifacts that are going on. Currently, our output is just to a very coarse triangle mesh. So right now, our stress results can sometimes look a little bit weird because we're not doing anything fancy with our results. So that's something that will improve as we move forward. But you can actually even see some of the triangles of the output tessellation. Anyway, so I think we'd like to ask a quick question of the attendees now. Now that you've seen this. So the question is, what is the longest time that you have spent cleaning up and meshing a single part of an analysis? We'll maybe leave this up for about maybe 10 more seconds or so. Right, I'll go ahead and end it now. And then I'll share the results out to folks. So it looks like a majority of folks are spending on the order of hours or days to mesh a single part for the longest time that they've spent meshing a single part. And I personally am extremely jealous of whoever said that the longest they've ever spent was minutes. And I'm sure that many of us are envious of that person as well. And a couple of folks who've taken maybe weeks or even months to mesh a single part. So thank you all for participating in that quick question. So now I'm going to introduce some of the Coreform IGA technologies, the U-Splines and the flex representation method. But first is one additional comment, just why Coreform IGA. If we kind of look on a grid or an axis of how long it takes to solve a problem versus how accurate the solution is that you're getting out, there's kind of like this is notional, I should say, but we kind of have traditionally seen hex-based FEAs taking the longest to prepare, but is the most accurate and the most robust when you have really challenging problems. And then there's, TEP-based FEA, there's a variety of different meshless methods and voxel-based methods. Again, these are just notional where they're at, but generally it seems that there's this general trend that the quicker it is to prepare the model, maybe the less accurate, maybe the less robust the methods tend to be. And so with U-Splines, which we're about to introduce, there's this ability to have even higher accuracy because we can now use higher order elements effectively for analysis. And so that allows us to take the traditional hex-based FEA approaches to build body-fitted U-spline meshes, which are then much more accurate. And because they're a bit more efficient, they're also a little bit faster. But we can also now take these meshless methods and use immersed splines to now get really high accuracy and still be very fast. And that's kind of in this realm that we're trying to develop solutions for with Coreform IGA. That just kind of hopefully notionally gives an idea for where we were targeting or the space we were targeting with our technologies. So without further ado, so the first of those technologies then is the U-spline, as I suggested before. And so U-splines they're a novel spline construction, but they're really not that much different from the B-splines and NURBS you've seen previously. They fulfill the same vision. What's neat with U-splines is that all it requires is for the user to provide a mesh and then their desired spline properties, such as what the degree of the element should be and what smoothness they wish to have in between. And so then from those, we get out this Bezier extraction format, which I alluded to previously, which allows then researchers or traditional FEA codes that are able to read that format and know how to process it can then use splines in analysis, as well as in the control points that fit the geometry. And so what's interesting is if you look at B-splines, which, the B stood for basis, this really is a fulfillment of the original vision of B-splines, in our opinion. And we actually we have a paper that's been published in Computer Methods in Applied Mechanics and Engineering, also known as CMAIN. And so there's a link down there if you wish to find that and read about it. So I think it's electronically available right now. I think it'll be published paper soon. And the key thing with U-splines is we developed them not only to be suitable for defining CAD surfaces, but also that they're suitable for analysis. And so this is a couple examples, a surface mesh that you might use for maybe a boundary element method or for like an electromagnetic calculation that has hierarchical refinement of the U-spline to provide local adaptivity, as well as in a volumetric U-spline on the right here for the simple tensile bar plasticity problem. So then we leverage those U-splines in our flex representation method. And the key with the flex representation method is it gives us the benefit of being able to do fully immersed models, but also because we can use unstructured splines, that allows us to now maybe only locally immerse, and in some regions be body fit or boundary fit to a region that may be a high critical or critical region of our analysis. And so here you can see maybe we really need to get fast convergence in this region, so we can body fit here and then immerse elsewhere. And then we inherit all the different properties that U-splines then provide us. And so what that's kind of allows us to do is now start to build out the spectrum of solutions that the engineer has available to them, from the traditional FEA or traditional IGA approaches, which may involve it's fully body fit, but it may involve defeaturing of your model to be able to build a mesh, or the traditional fully immersed problem with, again, no defeaturing that's had to occur. You kind of see here that there's some shoulder fillets that were defeatured in this region. But then again, this locally immersed paradigm where we can say, maybe I want to, for efficiency purposes, I want to maybe be boundary fit to the outer radius of this piston, or maybe even the only region that was hard to mesh were these two shoulder fillets. So I can just locally immerse them and be body fit everywhere else. And then it's really fast to build the mesh, but still very efficient because the amount of immersion is minimal. And there's a couple examples then of using flex representation method. This is a C-frame problem, and we've done a traditional FEA approach on the bottom right, and then a FRM approach on the bottom left. What you're looking at the bottom left are actually the quadrature points. This is an old figure, just we haven't updated with the surface. But the key is that I've got this complex geometry with all of these complex fillets, and as opposed to having to defeature them or spend many hours trying to build a conforming hex mesh, we're just able to immerse it in kind of a locally immersed mesh that's like this horseshoe that captures all those, like the main features of the model, but immersing the minor features. And then because we have U-Splines, we can then build this high order basis, so like a cubic, and we converge really rapidly to a solution. And if you compare to traditional FEA approaches, where traditional FEA approaches are predominantly linear hexes, especially for nonlinear problems, you can see that we're able to essentially converge to a solution several orders of magnitude fewer elements than might otherwise be required. And then another example, and this is going to parlay into the GE engine bracket problem. This is a sizing optimization example for a wheel. And what you can see on the left is notionally what we have some boundary conditions in the purple and the green that we want to hold fixed. This is a rigidity test. We're going to push on the orange region and look at the deflection of this wheel. And then we want to minimize the mass of this wheel in our sizing optimization. The lower that we can reduce the mass, actually, it really helps out with fuel efficiency. So again, with our FRM model, we can immerse it in a locally immersed model that captures the general cylindrical shape of our wheel. But then all the sub features are just going to be immersed. And that will allow us to then change the size, which may end up changing some of the CAD topology, which we can see here actually. So this is now on the back side. This was that, we're looking at the green surface on the back side. As I change in this case, the width of these spokes, this region here suddenly eats into that surface and it changes the topology. And with traditional meshing workflows, if you'd done a hex decomposition approach, you would have to remesh, and you might have to even completely define a whole new meshing algorithm, like scripting, to get your hex mesh maybe to conform to these surfaces. And so, in fact, we oftentimes don't worry about that. We just build a tep mesh. It's even robust to, in this case, the geometry, the CAD software that the customer is using failed to regenerate one of these pockets. And that might cause a failure in your meshing workflow. And actually, in our case, we're actually able to, I mean, it's an invalid geometry that we probably want to throw out anyways, but it's just interesting that the flex representation method is able to capture, or it's impervious to this change in geometry for its analysis. Okay, so I might pause real quick, Matt, for a couple of questions before I talk about the verification workflow. So
Yeah.
are there any questions I should maybe answer before we move on?
Yeah, why don't you go on ahead?
Okay. All right, so now we're going to show, the key here is we're not going to do topology optimization. We're going to verify, or the goal here is to verify the results that came out of an optimization. So this is some of you may be familiar with this problem. I think we have some folks from GE actually on here, but in 2013, GE sponsored a challenge project, which you can find on GrabCAD, which was to take a traditionally designed and manufactured engine bracket and with certain load cases to design improved or optimal brackets that might use topology optimization or just really smart people to come up with unique designs. And they had 630-ish entries that were submitted. And what we want to do is that traditionally you do a topology optimization, and then you want to do a verification study of the optimal or the computed result, just to make sure that, if we actually then run it through these load cases separate from the optimizer, get the same result. You might then do some cleanup of your STL file to maybe put smooth surfaces over it, or you might use it as inspiration for maybe a more traditionally manufactured part, and you would want to do a verification again on that model. And so that's what we're going to show here, is like that verification stage. A couple outcomes, though, that we found in one of their white papers that they presented at Solid Freeform was that some of the models in STL file were so large that they couldn't even mesh these models. And then actually the evaluation of these 600 plus entries the bottleneck became GE's ability to actually do the evaluations. And so that's maybe like an inspiration here is, could you potentially run all 630 models automatically in a single workflow? And at Coreform, we think the answer is yes, in that what we've done some initial demonstration on is being able to take, in this case, this is the winning bracket that's then immersed in an envelope geometry. And we can then perform the calculation on top of it. But not only can we run just that one model, but we can actually run any of those models because they fill the same design envelope. They all fit within that same background grid, and we can then compute results on them without having to worry about, TEP meshing or trying to decompose for hex meshing. We're just able to use that same base approach for all of them. And because the surfaces still exist, right? They all have like these two holes for holding the pin and then for the bolts. We're able to, and we'll show actually this process, but it becomes trivial to grab those surfaces and apply your boundary conditions onto them. So I'm going to get ready for the live demo. If just to kind of show what we're talking about here, if Jessica, if you want to start the second question and maybe introduce it while I get the demo ready or switch over.
Yeah, so here what we're just curious about is how you usually set up models for simulation. Are you usually using a GUI, maybe perhaps using a GUI and then making changes through a text editor as needed, or exclusively through a text editor? Go ahead and leave this on just for a couple more seconds. All right. So here's the results. It seems like the majority are, well, the majority are using a GUI, and a good chunk as well are making minor changes through a text editor as needed after the initial GUI setup. So we'll be sharing some of where we're at today as well with that workflow here.
Yeah. So thanks, Matt. So this is showing this example here. This is again, the baseline model immersed in this case in an envelope domain. And I'm going to show now, I'm going to get rid of the envelope domain. I'm just going to show the baseline. So again, if what we want to do is we want to create our boundary conditions, so I'm just going to create a couple of groups to hold them. So I'm going to create a group called hold bolts and a group called maybe load surfaces. So then using Cubit, we can come in here and say, select the surfaces that we want to apply our boundary conditions onto. We can use some of the tools like saying select similar surfaces to automatically then find equivalent surfaces elsewhere in our model. And then we can add those to our group for the boundary condition. And I can do the same for those load surfaces as well. And apply those to a group, this load surfaces group. And now they've been assigned. And really, that's, I mean, I'm like done with that model prep in terms of meshing. I've got my envelope domain, so I can actually go ahead and redraw that envelope domain. I can put a mesh on it, maybe refine the mesh a couple of times if I want. And so that I can maybe get a more accurate result. But that's really all that's required from that kind of prep process. As a quick note, let me just fill this up again. One. Sorry about this. Let's see. Well, anyways, what I can show is that because we've actually got all of those models all fit within the same space. Do this. There we go. We have them all within the same space, so you can kind of see they're all overlapped. So I could say we can look at, say, in this case, this is the winning entry, and these are actually like the top, I think, 7 results. But because they all fit that same space, that workflow is the exact same for all of them. I've got those, I've got those bolt surfaces, I've got the load surfaces all selected if I want. So it becomes trivial to do that, again, to do that setup. So we're also building tools. I'll just show briefly. This is kind of a work in development that we're building, kind of a streamlined workflow to allow for folks to then prepare their Coreform IGA simulations inside of Coreform Cubit, as well as to create their boundary conditions and be able to export this out to a solve. I'm not going to show that part today because we're currently working on building some improved interactions for that, but I will show out some results here. So again, this is in this case, the baseline. We're showing displacements here. And so this is kind of like the compliance of these results. And so there's maybe a 0.28. I think these were done in, in inches, I believe is what we performed this in. It might've been done in millimeters, but just in these other results as well, that because they have less material, they have larger deformations to go along with them. But again, it doesn't really matter if that part is a complex part with a lot of holes and a lot of organic surfaces, or is that really blocky surface? The process is the same for all of them. And then because that process is the same for all of them, one of the things that we're also able to do is then automate this. And so if we wanted to do all 630, so I've just got like a simple little Python script. Cubit allows for Python scripting. We can say every command that you do actually in Cubit can be accessed through a Python API for Cubit. And those get generated as you're operating in Cubit. So that helps you build up these scripts really quickly. And so this is a case where I can really rapidly prepare that model. Obviously, I could functionalize this, so I could do all of the different entries individually if I wanted. I could do even higher levels of scripting. There are some temporary files that get created that for advanced users who like to work in a text editor, you might find yourself preferring to maybe do some editing just directly in these text files that are a JSON format. And it's the same for our solver as well, that it's in a human readable and machine readable JSON format. Allows you to kind of quickly see what things are going on and be able to change values if you wish. But because we're applying those boundary conditions again to given sets, like the fixture bolts, as a user, you don't actually have to really come in and do anything to run that new model. And then the automation can then be fully done here, done like bash scripting. Again, we can automate this with a sophisticated Python script. But all I have to do is prepare the model and then run my simulation. And it doesn't matter if I did it for the baseline model or for any of those optimized models. Again, I've listed them out here in brute force fashion, but this could also be done very sophisticated, either in Bash or in Python. And so when I ran all these models, so you can see here I ran, the 5th place was missing from the GrabCAD database. So actually, I think I only ran 8 models, but I was able to just set it and forget it, and they all provided results without having to have any manual intervention. So I think that does it for the live demo portion. And I think that's all we wanted to share in our webinar today. We're happy to take questions, and thank you again for your attendance.
Okay.
And yeah.
Great. Greg, thank you very much. We've got a few questions. One, how can we try Coreform IGA?
Yeah. So, Matt, do you want to answer that?
Yeah, I mean, just go ahead and reach out to us. So we'd be happy to work with anyone to get this up and running for them that looks like you have problems that this would address. See, another question. What this file that you were using was a CAD file. Is there any other input file format that Coreform IGA can read, any other data types?
Yeah, so Coreform Cubit, essentially, as long as Coreform Cubit can read it in, we can operate on it. And so we do have a fairly sophisticated amount of formats that we can read in. We have plugins to read other like CAD formats, but you can also read in like STL files if you prefer to work with, because oftentimes that's what you end up receiving are STL files. We're also working with some partners on looking at like implicit representations, which are commonly used in topology optimization, in lattice structures, and some various complex surfaces. So we don't have that part functional yet, but we're looking to. Our goal is that we want to be able to support pretty much any data format or file format that you might be working with.
Thank you. Can you simulate interactions between parts like contact?
Yeah, yep. So we do support contact. We support both self-contact and defined surface-to-surface contacts. And that is something that, contact is, so contact and fracture are probably the two most challenging nonlinearities in structural mechanics. And so there's a lot of work we're currently making in terms of improving contact and making it more efficient, more robust, making the workflow even faster for users. So it's improving all the time. But we do today currently have contact capabilities. Yes.
Okay, thank you. Let's see. There's someone raising their hand. If you want to type in a question, then feel free to type it, then we can read it and address it. Let's see. What is the approximate runtime for these engine bracket simulations?
Yeah, that's a great question. So I mentioned earlier that we're building Coreform IGA on these high performance computing libraries. So while we have, PETSI as a parallel solver, we actually so far haven't actually hooked up to any of the parallel compute capabilities. So we're solving on single cores with a direct solver, which is where we're spending the majority of our time today. So, and just to give some perspective, these models had approximately 200,000 to 600,000 degrees of freedom based on like how complex the models were and how organic they were. And we're able to solve, so in the scripting sense, the full prep to solution time, it would vary anywhere from about 15 minutes to about an hour with kind of those caveats in place. And so again, with those caveats being single core, direct solvers, and in the hundreds of thousands of degrees of freedom area. So we're expecting to get more performance, especially as we just even enable parallel compute and iterative solvers. But that's where we are today.
All right. Here's another question. Can you give me an idea about the material library and the constitutive models available in IGA analysis? Can hyperelasticity and plasticity be included in the analysis?
Yeah, so today we have a pure linear elastic material model, as well as a nonlinear elasticity, so neo-Hookean elasticity model. And we also then have an isotropic plasticity model. One of the things I think is unique with Coreform is that our user material interface is written in Julia. If you're not familiar with Julia, it's a language that looks very similar to, say, MATLAB or Python, in that it's dynamically typed as opposed to maybe like a C++ or Fortran, and it's just in time compiled, so you don't have to like worry about having a separate compiler. And so we've had some folks who've implemented like rate dependent plasticity models in that Julia interface. I think like a Johnson Cook material model, I think one of our partners or customers had implemented using that interface. So we're always interested to add more materials. It's just something we've not spent a lot of focus and time on yet. But if you have material models that would be valuable to you, we'd be happy to add those.
Okay, all right. Well, Greg, thank you very much. And thanks everyone for attending today's webinar. All of the development at Coreform with Coreform IGA is motivated by customer problems. And so if you see anything here today that looks like it might be applicable to issues that you may have, we'd love to talk to you and start directing our efforts so that they can support you as well. So with that, hope everyone has a wonderful day, and we'll see you at another webinar.